Lecture notes for Chapter 5, Work, Section 2. In Section 2, we're going to look at machines. So what is a machine? Well, a machine is a device that makes doing work easier. Machines can be simple, and basically that's what we're going to take a look at in this chapter, and it's going to be the basis of your Rube Goldberg machines. Some, like knives, scissors, and doorknobs, are used every day to make doing work easier. Machines can make work easier by increasing the force that can be applied to an object. A second way that machines can make work easier is by increasing the distance over which a force can be applied. These are always good test questions. Or, machines can also make work easier by changing the direction of an applied force. A car jack is an example of a machine that increases an applied force. The upward force exerted by the jack is greater than the downward force you exert on the handle. The jack goes up in this direction, and you're pushing down on the handle. It doesn't take this as much force as you get in lifting the car. However, the distance you push the handle down is greater than the distance the car is pushed upward. And any of you that ever used a jack, you know this is true. The jack increases the applied force, but doesn't increase the work done. Force and distance. The work done in lifting an object depends on the change in height of the object. The same amount of work is done whether the mover pushes the furniture up the long ramp or lifts it straight up. And we've seen that in problems, when you work the problems, that this isn't necessarily true. If the force is the same and the distance is different, then using a ramp produces more work. If work stays the same and the distance is increased, then less force will be needed to do the work. Some machines change the direction of the force you apply. The wedge-shaped blade of an axe is one example. When you use an axe to split wood, you exert a downward force as you swing the axe toward the wood. In other words, this is the direction of the force, but this force is translated in this direction. So that's what the machine is doing, using this downward force, but creating this work. The blade changes the downward force into a horizontal force that splits the wood apart. When you use a machine, such as a crowbar, you're trying to move something that resists being moved. If you use a crowbar to pry the lid off a crate, you're working against the friction between the nails in the lid and the crate. So you're applying a force as arrows indicate in this direction, but it's transferred in this direction. You also could use a crowbar to move a large rock. In this case, you're working against gravity, the weight of the rock. Two forces are involved when a machine is used to do work, the input and the output forces. The force that is applied to the machine is called the input force. And later on in the chapter, we'll work some problems, and you'll see where this becomes important. Fin stands for the effort force, or the input force. The force applied by the machine is called the output force, symbolized by F out. Two kinds of work need to be considered when you use a machine: the work done by you on the machine and the work done by the machine. The work done by you on a machine is called the input work and is symbolized by W in. The work done by the machine is called the output work and is abbreviated W out. When you do work on a machine, you transfer energy to the machine. When the machine does work on an object, energy is transferred from the machine to the object. The amount of energy the machine transfers to the object cannot be greater than the amount of energy you transfer to the machine. A machine cannot create energy, so W out is never greater than W in. So you never get more work out of a machine than the work you put in. And later on we'll talk about efficiency. A machine cannot be 100% efficient. When a machine is used, some of the energy transfer changes to heat due to friction. The energy that changes to heat cannot be used to do work. So W out is always smaller than W in. An ideal machine. Suppose a perfect machine could be built in which there was no friction. None of the input work or output work would be converted to heat. For such an ideal machine, the input work would equal the output work. So W in would equal W out. Suppose the ideal machine increases the force applied to it. This means that the output force, F out, is greater than the input force, F in. Recall that work is equal to force times distance. If F out is greater than F in, then W in and W out can be equal only if the input force is applied over a greater distance than the output force is exerted over. Mechanical advantage. The ratio of the output force to the input force is the mechanical advantage of a machine. Mechanical advantage of a machine can be calculated from the following equation. Mechanical advantage equals output force in newtons divided by input force in newtons, so that MA equals F out divided by F in. And mechanical advantage is a number. It doesn't have any units. And we'll see that when we get to some problems related to mechanical advantage. Window blinds are a machine that changes the direction of an input force. You pull down on the string, and the curtains go up. A downward pull on the cord is changed to an upward force on the blinds. The input and output forces are equal, so the mechanical advantage is 1. You pull down, the curtain goes up with the same force, so the mechanical advantage would equal 1. Mechanical advantage of a machine without friction is called the ideal mechanical advantage, or IMA. IMA can be calculated by dividing the input distance by the output distance. And again, we'll see some problems later on in the chapter related to mechanical advantage. Efficiency. Efficiency is a measure of how much of the work put into a machine is changed into useful output work by the machine. A machine with high efficiency produces less heat from friction, so more of the input work is changed to useful output work. To calculate the efficiency of a machine, the output work is divided by the input work. Efficiency is usually expressed as a percentage by this equation. Efficiency in percentage equals the output work. Work is measured in joules, divided by the input work, also measured in joules, times 100%. So efficiency equals W out divided by W in times 100%. In an ideal machine, there's no friction, and the output work equals the input work. So the efficiency of an ideal machine is 100%. The efficiency of a real machine is always less than 100%. Nowadays, in new appliances in your home, if you got a new appliance recently with a yellow sticker on it, it might say that that machine is maybe 90% efficient. It can never get to 100%, but a lot of new machines, appliances are getting close. Machines can be made more efficient by reducing friction. This usually is done by adding a lubricant, such as oil or grease, to the surfaces that rub together. A lubricant fills in the gaps between the surfaces, enabling the surfaces to slide past each other more easily. This concludes the lecture for Section 2. We'll go through the questions. After you complete the lecture, remember to go back to your MyBigCampus account and complete the section review. Question 1 asks, what do a knife, a doorknob, and a car jack have in common? The answer is they're all simple machines because they're devices that make doing work easier. Question 2, when a machine is used to do work, the force that is applied to the machine is the correct answer. It's the input force. Question 3, what is the effect of increasing a machine's efficiency? The answer is increased efficiency increases the amount of input energy converted to useful output. This concludes the lecture for Section 2.